Yeah. Yeah. That kind of weirded me out a lot. Okay, so this is AP Chem Review, thermodynamics.
Sequoia Holmes, please come to the K-Wing office. Sequoia Holmes, please come to the K-Wing office.
So with thermodynamics, probably the first thing you want to remember is that what's the difference between a state function and a non-state function? So state functions are path independent. And the state functions are delta H, delta S, delta G. And if you don't remember, H is enthalpy, which is a measure of heat in the reaction. Delta S is the measure of disorder in the system, and delta G is the Gibbs free energy. In other words, the amount of energy you have free to do work. Some sort of work. We can also add on here the energy of a system, and depending on the book you use, it might be delta E, or they might call it delta U, but they're the same thing. It's the total energy in the system. Non-state functions are path dependent, and that is Q and W. So when we calculate Q, we're typically using the equation mass times the change in heat times the specific heat. And for work, we're typically interested in pistons moving up and down in gases. So negative P, change in volume. And the pressure is going to be in kPa, because in order for work to be in joules, your answer to be in joules, a liter times a kPa is a joule. So your pressure will have to be in kPas. And your change in volume is final minus initial. Okay. The total energy change in the system is the addition of these two. So we would say the total energy change in the system is the change in heat plus the change in work. So depending on how you set up the experiment, Q and W can be different. That's why they're path dependent. But if you measure heat at constant pressure, we call that enthalpy. So delta H is measuring Q at constant pressure. So, I mean, it really, they give them different names, but you really just want to think of delta H and Q as the same thing. They're measuring how much heat is given off of a reaction. If heat's given off, it's exothermic. Heat is absorbed, it's endothermic. Okay.
Just a reminder, there is a VAEA meeting that begins at 4 p.m. over at Badger Ridge in room 201. Again, a VAEA meeting beginning at 4 o'clock in room 201 over at Badger Ridge.
Delta S is the change in disorder in a system. And we want to go from order to disorder. And it's kind of the opposite of delta H in that we want delta S to be positive. That means you're going from order to disorder. And if you have a negative delta S, you're going from disorder to order. So we want to go to disorder. We don't want to go to order. And let's just see if I can get see if you can tell me what the delta S sign would be for something like
King,
this.
please call 4405.
That was a kid.
It was a really young teacher.
Really?
How about we take, I'm just gonna make up the reactions here. Balance this, we're gonna need a 2 here, 6 here, 3 there, and 2 there. So, what's the delta S on this reaction going to be? It can be positive or negative. So, what has high order? Solids, liquids, or gases?
Solid.
Solids have high order. So, liquids have some order, not as much as solids. So we have 2 moles of solid, 6 moles of a liquid, going to 2 moles of an aqueous solution and 3 moles of a gas. So this side is going to be much more ordered because I've got a solid here in the liquid. This side, I've got a gas, is going to be much more disordered. So the delta S of this would be positive. What about, let's say, this reaction? Two moles of hydrogen gas plus 1 mole of oxygen gas going to 2 moles of water vapor gas.
Do you have to look up the delta S or not?
No, I can pretty much figure it out. How many things do we have, how many moles do we have on this side? 3. How many moles do we have on that side?
2.
3 things are combining to form 2. Is that becoming more disorganized or more organized? More organized. So delta S is going to be negative. Now, I purposely picked them all to be gases, right? Because that way, if it was, something like, up here, if this was not very common, but let's say that was a gas. 6 moles of gas and 2 moles of a solid, it becomes less clear as to what the answer would be. So typically when they give you a problem like that, it's going to be all one phase and you look at the mole ratio and like, oh, okay. Or you've got a lot of solids on one side and you know that solids are highly ordered. So anytime you break down a solid, that's going to be the case. So positive delta S, that's a good thing. Negative delta S, that's a bad thing. Positive delta H means you're endothermic. Negative delta H means you're exothermic. So this is, you want to be getting heat out. You don't want to have to put heat into it. So what happens if, you know, your delta S is negative, but your delta H is also negative? Who wins out? That's where you have the Gibbs free energy equation, which relates the two together. T is almost always, T is at 298 for our purposes. We're at standard conditions, so that's what the little circle means. The standard conditions is 25 degrees Celsius. If you change this temperature, you change these values, okay? But for AP Chem, they usually say, okay, you're changing the temperature, assume that the delta H's don't change, okay? Because in order to recalculate the new values, you have to know differential equations. So, what you know. So, if delta G is negative, what does that mean?
Reaction is spontaneous.
Yep, spontaneous. And if delta G is positive, then it means
Not
it's not
spontaneous.
spontaneous. Can I erase this top part? So when calculating delta H, the assumption is that the delta H information of all elements are 0 in their most common state. So anything like potassium solid, delta H information would be 0. Delta H information of chlorine gas would be 0. But the delta H information of monatomic chlorine gas would not be 0. Because the most common state of chlorine, the element chlorine, is diatomic. So if you change it to monatomic, something that's not very common, it's not going to be 0. And you have to look it up in the table. Okay, so elements in their most common states. If it was liquid chlorine, it would not be 0, okay, because it's not the most common state. And so you look up the delta H of formations, and you use that then to calculate how much heat is released in a reaction. So if I had a reaction like CH4 plus O2 balance it out. I'll need a 2 here. And I think that's good. No, I need a 3 halves here, because I need 3, no, I need 2 there. So to find the amount of heat released from the reaction, you do the delta H of formations of the products minus the delta H of formations of the reactants. So you gotta look up those delta H of formations on the chart. And so that's kind of one of the problems they'll do, is they'll give you these 3 values in the chart, but not oxygen. But you know the value of delta H for oxygen, you know it's 0, because it's the element in its most common state. So that's how you do it. And it's basically the same thing for delta G. We would say the delta G of formation of elements is 0 as well. So if you want to find the amount of free energy reduced, given off by a reaction, you would do the same thing. Find the delta G of formation of products minus the reactants. And you multiply them by their molar ratios. So whatever the delta H formation of water is, multiply it by 2. And make sure you're using the correct water, whether it's liquid or gas, because they have different values. Okay. Let's see. That's pretty much it for chapter 6. Do you have any questions?
Is there, one where you do reactants, mass products, or am I making that up?